scale goes from 10 is really, really bad to 1 which you don't feel. Okay? They then take the population of each of the cities and tell you how many people or what strength these people felt the shaking at. And they present it this way. Sorry, this is a bit small, so I'll make it a bit bigger for you. So first of all, they map out what the shaking looked like, and then they produce for each Mercalli intensity the number of people who experienced it. So there were 9 million people experienced intensity 6 here, for example. There were only 250,000 people experienced intensity 9, and nobody got shook at intensity 10 for this earthquake. Okay? What I'm now going to do is I'm going to say there is some weighting which tells you how bad a 10 is compared to 9. And I know that the scale is approximately logarithmic. It's not exactly logarithmic, but it's something like that. So I'm going to set the weighting for the intensity 10 at 1. That means the intensity 9 is about 0.1, and 8 is about 0.01, and the whole way down you can scale it that way. And then I've got a really clever statistician, really smart girl, who's doing this properly and doing the best job she can on the statistics. I'm not going to talk about her anymore. But basically, I then take the number of people and multiply by the weighting, and then I add the answers for all the different intensities. So I've got the number of people, I've got the intensity, and I've got the weighting for that intensity, and add it all together and it'll just give me one number. And the number is a measure of the amount of shaking and the number of people who experienced it. Simple. Okay? And then I start playing about with some social variables, but basically I'm going to call this shake potency. It's how bad an earthquake was, both in terms of shaking and in terms of the number of people who experienced it. And then I'm interested, of course, in the number of deaths. What would you expect this to look like? Well, earthquakes that shake a lot of people hard are likely to kill more people, so you would expect to see this type of trend. Okay? And there's what we get for the 618 earthquakes that have killed 1 or more people in the last 30 years. Okay? And I color code the things by GDP. Now, what's interesting about this is, well, first of all, there's something that looks as if it might be interesting. It's actually quite boring. All the rich countries cluster down here. In other words, even in big earthquakes, they don't get many people killed. That's actually not very interesting. We knew that. Okay, Americans and Japanese people don't get killed in earthquakes generally. What's more interesting is that there's a lot of blue dots down here as well. In other words, there's a lot of really poor countries suffering really big earthquakes, and very few people are being killed in them. So we thought, well, let's try and break this up in terms of countries, see if anything comes out. And there's what you get. These are all blue, they're all poor. The Philippines cluster down here, and the Iran is a big spread, but nearly all the worst earthquakes happen in Iran. So there's, despite the fact they have the same GDP, the Philippines are doing something to protect the people and the Iranians aren't. Okay? We take this a step further, and I'm finishing in another 1 minute. And from that previous diagram, I can now take for each of these earthquakes and measure an index that tells me how vulnerable the people were for that earthquake. How does that work? I take the number of people who were killed by it and divide it by the strength of the earthquake, that it was. If the people are really vulnerable, a lot of people will be killed by small earthquakes, so that number will be very big. And if the people aren't very vulnerable, even big earthquakes don't kill them, so the number will be small. And then you ask, if I plot this measure of vulnerability against the GDP, the amount of money that the country has, what would you expect? Well, poor countries should have a lot of people getting killed. Rich countries shouldn't, so the plot should look something like that. And when I do it, I find that. Now, I find this absolutely amazing. First, just as we expected, Iran's really bad. Turkey, Italy's pretty bad too. The amazing thing are these two countries here. that somehow Indonesia and China have this is education, so we've been playing around with a few different things. But basically, India and China have a similar per capita GDP, and yet there are far more people being killed by earthquakes there, and somehow the Philippines and Taiwan are doing something that's protecting their people, despite the fact they don't have any more money. Now, I work in the Philippines occasionally, and it turns out that they have one of the most well-developed legislative frameworks for disaster risk reduction, mainly for typhoons, but also for earthquakes, landslides, and volcanoes. So just the amount of effort that they're putting for the same GDP into preparing people seems to be making a difference. And what we're going to try and do now is see if we can learn from these countries and individual earthquakes and go and talk to our friends in Indonesia particularly and see if some of the lessons here can be used systematically to try and pull Indonesia down to the lower level. And I'll just end with hope. This is an earthquake on the 10th of April 2005, 6.4, absolute mad chaos in Padang City. There were half a dozen people killed, being trampled to death by people trying to evacuate the city. This is the September 30th, 2009, actually, that's a typo. And we are led to believe there was a pretty orderly evacuation, and neither of these earthquakes produced tsunamis, but people would have survived better in 2009. Thanks a lot.
Thank you for the question. If anyone with a question, should take that.
You asked about slippage, like that the two land masses moving across each other. You said some of them were moving free and others were. Is it something to do with what the geology of the material? Is that it?
That's a great question. The honest, straight answer is we don't know, but there are some good guesses. First of all, where the islands are, the pressure on the fault because of that extra topography is higher. So the normal stress, which is part of the friction problem, is bigger. So it's definitely related to simple things like that. We also know it's got to do with fluid pressure within the fault zone. So where fluids are existing at high pressure in that interface, they lubricate the fault. That's part of the question as well. There are temperature differences along the fault that are more complex, and that's part of the problem. And finally, and I could probably go on, but there are also big fractures in the plate that's being subducted. And where the fracture hits the interface is places where you generally get low coupling. So somehow they're bringing material or maybe fluids from depth. So there are four probably of the front runners, but we don't know.
But just along that fault, did you see that stick slip in the slide, or can you see that Manitoulin fault as well, and other faults along?
I haven't seen the results of anybody doing this type of work for the North Anatolian fault. People have seen it for many years in the San Andreas fault. We know that probably there's about 50,000 kilometres of subduction zone around the planet. We've probably done this work on about 5,000. So it's something that people understand is a really important part of the problem, but we've only, the first paper on this was published in 2006, so it's really young, and we haven't got the data collection. Sumatra is very poor compared to Japan and Chile, but it's still in the top 5% in the world. So we need better data, and we need to answer that type of question. Because it's only when we understand that we'll be able to, we have any chance of being able to say what the next earthquake will be. But not yet.
John, I noticed that since the last time we heard this talking about the social scientists, have the social scientists made you a better scientist?
I am absolutely sure they have, because they have help me to believe that what we're doing is worthwhile. So you burn the midnight oil a bit more. The uncertainty that they kept talking to us about at the start is something we always knew about, but we were sort of sweeping it under the carpet. Now we're not doing that anymore. So I think it's an interesting question, it's a pretty good one, and the answer is yes. It hasn't helped us to solve the equations better, but I think we're asking better questions.
If slip deficit is such a big indicator of when and where an earthquake might happen, what kind of progress has been made in actually measuring slip deficit in these areas that are at risk?
Well, first of all,
And how do you do it?
Well, first of all, this is completely new. So the first time that this was presented, some of this, the first time it was presented was the step-up lecture when you guys asked me to come and do this. There are lots of scientists who don't believe what I'm doing. Not because they don't think that slip deficit is what we need to get to. It's just they don't believe we're going to be able to do it. And I'm sort of going, well, you know, what we have to do is really put up the straw man model, knowing that it's wrong and that there are weaknesses in our data collection and stuff, and that there's big holes in the information that we need to do this. But it's a way forward. Now, how do you measure it? Well, you can't measure it directly. It's just can't be measured directly, because no matter how far back you go, you don't know what the slip deficit was whenever you start your reconstruction. So it's absolutely forbidden to do this completely. But the thing that somebody asked me a question sort of like this in Vienna a couple of weeks ago. They asked me, what about that unknown field? And I said, I know that it will always be unknown, no matter how far back we go. But the longer we do this, the less important it gets. Because the slip deficit is absolutely bounded at something like 15 meters for this subduction zone. Because if it gets any more than that, the thing slides. Okay? So it's absolutely bounded at about 15 meters. But the total amount of convergence between the two plates is unbounded.